Welcome to the last talk on the last day of DevNation. I'm Christine Flood. I'm here to talk to you about garbage collection. In particular, I'm here to talk to you about Shenandoah, which is a garbage collector that we've been working on here at Red Hat. I like to say Java without the GC hiccups. Who here likes GC pauses? Yay! I was at a talk 2 weeks ago with the Google exec was up talking about what they do about GC pauses, and what he said was that they'll send out a query and they'll wait 95% of the expected time for it to come back. And if it doesn't come back, they'll just send off a query to another machine. And that's how they deal with GC pauses. They are the bane of any kind of quality of service guarantees, and we want to limit them. We want to make them as small as possible. So just like, if you were a kid and your mom gave you a spoonful of sugar to cure the hiccups, the cure for Java hiccups is Shenandoah. At least I hope it is. If you have done Java work, this is how most of the garbage collectors in OpenJDK work right now. Your Java threads run for, they get their stuff done, they're in their quality of service, they're working. And then they all stop to compact the live objects. And then they start up again. So if you have any kind of response times that you're trying to meet, you just fall off a cliff during those pauses because the machine is unresponsive. So what Shenandoah does, we still stop all the threads. Well, but what we do is we stop the threads and we do a little bit of work. We scan the Java stacks and look for roots. And then we start up again and we do a concurrent mark. We have a little pause again. We stop the threads. We evacuate the stuff that's pointed to from your stack, and then we start the threads again and compact the rest of the live objects while your Java program is running. This means that you're much more likely, when you send a query to this thing, to actually hit running Java threads. So I've been talking about Shenandoah for over 2 years. And this time I wanted to be able to show you some numbers. So here you can see I'm not picking on G1. I love G1. I worked on the original G1. I'm on the paper. It's a great garbage collector. It's evacuating objects. It's stopping the world to evacuate objects because that's a simpler thing to do. But it's the default collector in OpenJDK 9, and so that's what I ran up against. SpecJBB 2015 is a benchmark, and it measures both end-to-end throughput, which is max JOPS, but it also measures responsiveness. And that's what they call critical JOPS. And you can see from this that we are about 10% off on end-to-end throughput. So you're taking a penalty for responsiveness. But if you look at the critical JOPS, we are 7 times better. You're much more likely to get a response from the VM that's running Shenandoah. If you look at our total pause time, we're a factor of 5 shorter. If you look at our average pause time, we're a factor of 10 smaller. And if you look at the max pause time, I really don't want you to look at that because it's a bug and we've got a solution for it. But when I took these measurements, we were a factor of 3 better. But that number should come down. We really want. I initially said we were going to keep that number under 10 milliseconds, and I've backed off. We think we can keep the max pause time under 100 milliseconds and your average pause time around 10 milliseconds. So these are sort of interim numbers. We're still working. We're still moving stuff out of the stop the world phase and into the concurrent phase. So we expect these numbers to get better. But for now, they're kind of compelling already. So can we try it ourselves? This is the other big announcement. Fedora 24 came out this month. If you download Fedora and you run Java, Shenandoah is there. --+ UseShenandoahGC. So we've shipped. It's there. It made me so pleased. I set up my little virtual box and I downloaded Fedora, and it was there and it works. So try it out. And if you don't run Fedora, well, set up a virtual box and run Fedora, or you can download the sources from openjdk.java.net and play with it that way. How does it work? So what do compacting GCs do? This is an oversimplification, but it helps for the explanation. You can think of them as doing 2 phases. They trace through all the live objects, and so they trace the heap and they mark all the live objects, and then they go through and they compact the live objects into one end of the heap. I once had somebody describe it as imagining you can grab the roots of all the trees and pick them up and move them over. And that's pretty much what the compacting GC is doing. So in this picture on the red nodes, somebody made a binary tree and they've been putting nodes in and taking them out, and they've ended up with this situation where they have these 2 live trees and all of these dead nodes. So you go through and you mark all those gray nodes live, and then the second phase is you go through and you copy the live nodes to one end of the heap. So the reason I like this picture is because it demonstrates the 2 phases and it demonstrates the difference of Shenandoah. The marking of all those live objects, there are many collectors that do that, and I'll get to that in a minute. I'm stealing my own thunder. But the compacting of the live objects to all of one in a heap to give you one contiguous area to allocate in, that's what's new with Shenandoah. So concurrent tracing, what I just said, the marking of live objects, that's a solved problem. It uses a snapshot at the beginning algorithm. It's been used by CMS and G1 and Shenandoah. We just used the code that was there. The concurrent compaction, the compacting of the live objects to bring all the free space, make all the free space contiguous, that's only in Shenandoah. We're the only ones that do that concurrently. And it's really important, right? CMS does mark and sweep, so they'll let you allocate in the holes that are left, kind of like malloc lets you allocate in the holes that are left. But that leads to fragmentation, and it leads to poor performance. And by fragmentation, I mean that you have a bunch of spaces that are free. So you have, 200 megabytes of free space, but it's all in little chunks, and you can't find a 20 megabyte space to put the object that you want to allocate. So by doing compaction, you leave yourself with one big allocation area, and you can easily allocate that 20 megabyte object. So again, if I haven't said it enough, we are moving the live objects while the Java threads are running. So I stuck this here because I need to reference it later. So Shenandoah heap is region-based, kind of like G1. We break up the heap into regions, and we choose the regions with the most garbage, and those are the ones that we evacuate. So we mark the entire heap. We figure out what's live. We figure out which regions are the most profitable to evacuate, and those are the ones we copy out. So why is concurrent compaction complicated? And I drew this little quadrant thingy to kind of show it. You have 3 threads here that are all operating on the same object. They all want to set different fields of the object. And the GC thread wants to move that object. So if the GC thread just moved that object, these guys might be working on the old copy. They might be working on the new copy. The only way to have correctness would be to have some sort of massive CAS or transactional memory that lets you work on, anywhere in the heap. It's really hard to do in hardware to make that atomic. And even if you could do it in hardware, it takes a lot of time to find where in all those threads are those references. And there could be references from other objects in the heap too. So finding all of those references and updating them atomically would be very hard to do. So we've done what all good computer scientists do in situations like this. We've added a level of indirection. Oops. All right, so sort of what you kind of want to have happen, what I just described, is you have all these threads that point to foo, and then you have this magic atomic switch, and after that, everybody points to foo prime. But I just described why that's hard and why we can't do it. And even if we could do it atomically, still finding them would take too long. So what we did was we added this level of indirection. So you have all these threads that are pointing to this object, and there's an indirection pointer. And so whenever you reference that object, you go through the indirection pointer. When the GC moves the object, it does an atomic update on the indirection pointer, as you can see over there. And what that means is the next guy to access that object is going to go through the indirection pointer and get to the new copy. This is the whole idea behind Shenandoah. It's not new. It comes from a paper in the 1980s, but it works. And it's almost as good as having accesses go through, having the atomic update that we wanted. So when I proposed this talk, I was told, I want to see a read barrier. So I'm going to talk a little bit about what we need to do in the compiler to make this fiction that you're going, well, to enforce this discipline that you're going through the forwarding pointer. So without a read barrier, when you go to read a field in an object, you know the address of foo, and you go to read the address of foo plus the field offset. With a read barrier, you have to first read foo minus 8 and get that address, and then add the field offset to that. So here is the hardware instructions for what gets emitted from C2 for doing a read. So without Shenandoah, I just stole this. It was the first thing that came up. It's Java lang string equals, and it's trying to get the value of the field. So it knows the address of the object. It adds 10 to that address and moves it into RSI. And with Shenandoah, we first take the pointer that's in RSI, we add -8 to it, and we move the contents of that into RSI. And then we add 10 to that. So we've added an extra instruction to read the contents of the indirection layer. It's one instruction. Now, most of the time, when you're running this, it's pretty fast, because the compiler in Java is smart enough to put some instructions in this delay slot, in these delay slots between the move and the get field. So you're still getting work done in there, and you're fast. If you want the adversarial program for Shenandoah, it's chasing a linked list with, not doing anything on it, just reading the next pointer, reading the next pointer, reading the next pointer, reading the next pointer, in which case you have to pay this penalty for reading the forwarding pointer and then reading the next field and reading the forwarding pointer and reading the next field. And in that case, in the worst case scenario, it's about a 40% overhead. But you don't do that. Nobody reads through a linked list and doesn't do the compare, doesn't want to see, have I found the item, or do some computation on each element. And once you start to do that, the costs go down. There's still a race condition here, because if you allow Java threads to write to fields and the GC thread to copy them, there's this window in here where you have the possibility of losing a write. Because here you can see that the Java thread goes to resolve the location of the forwarding pointer, sees that it's at foo. Meanwhile, the GC thread copies foo to foo prime, and then the Java thread writes to foo, and you've lost the write because the new copy of it doesn't have it. And that's why we enforce copying write barriers. What copying write barriers are, okay, what copying write barriers are is that they will, if they go to write to an object and the object is in a targeted for evacuation region, they will first copy the object, and then they will write to the new copy. And that way, everybody is ensured that we're all looking at the appropriate copy of the object. And here's what the write barriers look like in Intel assembly. Basically, we test a flag to say, is evacuation in progress? Because if you remember that picture I showed a while ago, evacuation is only part of the time, right? There's marking, and then there's times when the Java's running and the GC isn't doing anything. So only when the GC is doing evacuation, we check, and if that's true, if that's not true, we jump right to the put field. So there's just a check in the write barrier most of the time. If we do have the write barrier active because there's an evacuation in progress, we'll have to make a call out to the runtime system. And the runtime system will say, is this copying out of is this in a targeted for evacuation region? And if so, we'll copy it and fix the pointers and start again. So most of the time, our write barriers aren't very expensive. Aren't those barriers expensive? Not as much as you would think. So we've spent most of the last year optimizing barriers. You don't need a barrier on new objects, because if the objects are newly allocated, they're going to be in the 2 region, and they're not going to need a barrier. We don't need barriers on immutable fields. We don't care if you read the class pointer from the old object to the new object. It's going to be the same. And things like array sizes and class pointers are like that. We don't need a read barrier on the second read of a different field, or even the same field, in the same method. Once you've resolved the object, you're fine. We don't need a read after a write. And one of the things that's sort of a serendipity for us is hoisting. And C2 did this for us most of the time. If there's a hot part of your code, like a hot loop, or pretty much any loop, C2 will pull the read barrier up out of the loop. So this is kind of a, well, what I did was I was in a hurry and I ran the Decapa benchmarks. And the ones I could run with a big heap that didn't do any GC activity were the ones I picked for this slide. And you can see that there are 3 of them that ran without any GC. So there's no concurrent marking, there's no young generation collections. G1 for a lot of the benchmarks forced a young gen collection because there were resource problems that it wanted to reclaim. So here you can see that our overhead of our barriers for these 3 applications runs from 2% to 5.5%. So when you looked at the previous slide and you saw a 10% overhead on SpecJBB, that was because SpecJBB was behaving in a generational fashion, and so our collector wasn't as efficient. But if you're just talking about the overhead of the barriers, they're pretty good. It's not that expensive. So why aren't we generational? If you're familiar with GC, everybody says generational GCs are the best thing since sliced bread. So the hypothesis is the observation that in most cases, young objects are more likely to die than old objects. I believe this was true in the 1980s. I'm not convinced it's as true now. In particular, just to be obnoxious, I wrote a benchmark to model a least recently used cache. This is actually a program that a customer was using, and they were getting hurt by the garbage collector. So imagine that you have a hash table that maps a string, a URL, to a huge amount of web content. And what your program does is it goes in, it gets a new URL, it goes to put it in the hash table, and it wants to take the one that was looked at last. Sorry, not most frequently, but longest to go in the past. And that's the one it wants to get rid of and put this one in. This is sort of, you know how pointer chasing was my albatross because I couldn't put anything in those delay slots? This is the albatross for a generational collector. Because these guys are going to be copying all of the URL, all of the data associated with that URL back and forth, waiting for it to die. And it's not going to die. It's eventually going to get tenured. And then it's going to sit in the old generation for a while, and then eventually it'll get collected. But the only way they're going to be able to get it back is by doing a full GC. Or in G1's case, G1 can do better, right? G1 can do a partial GC to get it back. But I ran against G1 again because they're the default collector, not because I'm picking on them. And you can see that Shenandoah was actually an order of magnitude faster for this little toy benchmark I wrote, just to show that there are real applications out there that aren't, well, just to show I can write a benchmark that's not generational, that models a real application. You can see that our total pause time was a factor of 3 less. Our average pause time was a factor of 5 less. And our max pause time, again, that's 44 milliseconds. I'm not happy about that. It could be smaller. Was a factor of 5, 6, something like that. So if your application does not behave generationally, and not all applications do, then having a generational collector is actually going to cause you pain. And there are lots of other examples out there of people who wrote programs that fell into this trap. So how does Shenandoah compare with the other OpenJDK collectors? This is a slide I show all the time, but I love it, so bear with me. In OpenJDK, there are currently these 4 garbage collectors. If what you're doing is you want to run 100 JVMs on your machine, you have a server machine, you want to start up a bunch of tiny JVMs, you're probably going to want to run Serial JC. It uses 1 thread, it has a small footprint, and it has minimal overhead because it's only the 1 thread. So if you've got, 100 megabytes of heap, it doesn't matter because the GC pauses are going to be small enough that you're going to be okay anyway. If what you want to do is calculate a fast Fourier transform or some other big computation, and all you care about is how fast do I get the answer, what's my throughput, That's parallel GC. You want the high throughput collector. If in the current ecosystem, you want to minimize your pause times, you want CMS. And that's because CMS does the compaction of the young generation, but it does an in-place collection. It does a concurrent marking and a concurrent sweeping of the old generation. So you're only paying the cost of copying the young generation at pause times. And if what you want is, you want compaction, so you want to avoid the fragmentation of CMS, but you want managed pause times, you want G1. G1 is really good. You can say, I want to spend, 100 milliseconds or 50 milliseconds in garbage collection. And G1, which is also region-based like we are, will pick the amount of regions that it thinks it can do in that time period. So if you've given it a reasonable pause time that it can manage, it will do its best to stay within that pause time and keep up. So what's next? I've been talking about this for years, and we've shipped in Fedora. We want to ship in Rail. We want to put it back up in OpenJDK 10. I want that so bad. And we're working towards making that happen, but it's not completely in my control. So we've spent some time thinking, what else can we do to make garbage collection better? So as I said, we're trying to shorten those pause times. There's stuff that we can move out. There's stuff we can do. We can do weak reference processing less frequently. That's part of those pause times that were ugly. We can do some root scanning before we pause the threads, and we're working on that now. So shorter pause times are in our immediate horizon. But what about Shenandoah 2.0? What comes next? What can we do to make this even better? Marking the entire heap takes a long time, and it touches rarely used parts of memory. G1 does this, CMS does this, we do that, but it's not really what you want, right? If there are objects that are there that are sort of squatting and nobody's accessing them, but they're going to stay around for forever, you kind of want to ignore them and leave them off to the side. And so the observation for Shenandoah 2.0 is that garbage is only created by stack changes or by writes to the heap. So if nobody is changing the references to those old objects over there, we're going to leave them alone. So we want to focus GC wherever the writes are happening. So we want to scan the stack, and we want to scan the heap regions that are getting lots of writes, and we want to scan the heap regions that are referenced by those regions. But we want to try and contain this into a smaller set so that we can do less work and get more stuff back. So for my LRU example that I showed, those writes that are happening in the hash table, which is in the oldest region. So what we would want to do is we would scan the hash table. Well, actually, now that I think about it, this isn't going to be great because the hash table is going to reference everything. But the idea is that you focus it on the areas that are being changed and the things that the areas that are being changed are pointing to. So we keep track of the writes to the regions, we focus on regions which have changed, and we collect region sets together. And I'm going to explain that last one a little bit better. So the idea is that we keep a table of inter-region references. If you look at this, you can see that region 3 references region 5, and region 5 references region 3. So the insight here, just like with a generational collector, you can collect just the young gen and leave the old gen alone by scanning the roots and scanning the young gen and scanning the card table that points to the young gen. We can collect just regions 3 and 5 by scanning the roots and scanning regions 3 and region 5. So we can do a subset of an entire GC in a cycle. And if we wanted to collect region 6, we would have to scan the roots and we would have to scan region 7 because that points to region 6. So instead of what I said before where we were picking the regions that had the most garbage from our concurrent marking, we'll be picking the regions that have had the most writes. So we scan the thread stacks and the other roots, we scan the entire region group, and the referencing regions, and that will be a partial collection. So we should be able to get the benefit of a generational collector if that's appropriate, or we should be able to get the benefits of a, everything lives for a medium amount of time collector. Is there a question? I lost somebody. So part of the idea is that the regions that reference each other will be collected together. And my theory is that that's going to help out on NUMA. Right? So imagine you had 2 NUMA nodes. And you have Java threads running on each of the nodes, and you have concurrent GC threads running on each of the nodes. By keeping the segregation here as much as possible, you can see that there are node 1 regions, and node 2 regions, and empty regions, and shared regions. By trying to keep the regions that are segregated to be NUMA node 1 regions and evacuating them together, we can try and keep all of the data that's referenced by NUMA node 1 on NUMA node 1. Wow, I finished this in a record time. Okay, so the takeaway message is that Shenandoah rocks right now for some applications. And we're going to get it. We're going to make it better. So what are the applications that can benefit? Anything that needs quality of service. Anything that needs fast response time, an interactive application. Applications with large heaps that can't tolerate long pause times. And as usual, if you want more information, you can go to our website. We have a mailing list, and you can mail the 2 primary developers. And we'd love to hear from you. We're looking for more benchmarks. Somebody just pointed out SpecJ to me, so we're going to try and run that. We've been running Elasticsearch and Infinispan. But if you have a benchmark that you like, that you want us to run, send it to me. We'll add it to our suite. We'll run it every time we build and make sure that we're making it better each time rather than pessimizing it. I think we can call it a day. Thank you, guys.